Okay, second chapter of vectors here. Things heat up as this chapter goes along, so I'm telling you, it's time to turn it up a notch. Really address this homework and really practice this out because things get a little more difficult here. Applications of vectors is what the chapter is called, and the first topic is called force as a vector. Those of you who have taken physics will have a slight advantage here, but I'm going to try and explain it in such a way that the people who haven't got the physics won't have too much trouble either. So, force is a vector. Geometric vectors can be used to provide a mathematical model for many physical phenomena. One physical phenomenon that is effectively represented by vectors is force. If vectors were only invented to deal with force, that would be enough. That's how good vectors and force work together. When using a vector to represent force, the magnitude of the vector represents the magnitude of the force. Well, yeah, the length of the vector, how long it is, will represent how much force you're pulling with or pushing with. And the direction of the vector represents the direction of the force. Very nice definition and very useful. The magnitude of a force is measured in newtons, which is abbreviated as N. This might be news to some people that haven't taken physics. The best way to measure force, and it's not clear right off the hop why that newtons is used to measure force, but you're just going to have to live with it for now, that newtons is a great way to measure force. On Earth, the force is defined as the product between the mass and the acceleration due to gravity. So it really is how much force something's being pulled with, not just how much you are made up of. For instance, somebody who's 100 kilograms, you know from if you went to try to pick them up, that would be very difficult to do. That's around 220 pounds. So to lift somebody up that's 220 pounds, that's very difficult. But if someone was like 10 kilograms, like 22 pounds, well, that's not so bad. There's a lot more force. Where does that force come from? The force comes from gravity. Gravity is what's pulling the person downwards. If somebody was weighs a lot more, they have a lot more force to them, then they're harder to lift. So the force of gravity, the force pulling them down, is bigger because of gravity. And that's why the force has these two pieces to it. One is your mass, and two is what is the force of gravity, what is the acceleration due to gravity. And in the case of the planet we're on, Earth, that's 9.8. Now, the resultant of two or more forces is the single force that has the same effect as the forces acting together. Well, that's sort of a duh type definition. Yes, when we want to know what the sum of two forces is, when we put them together, the sum of the forces will be the resultant. To give you a small example, and by small I mean it's not too complicated what's going on here, but the math is a little wild. There's a lot of crazy math that comes out of this, and so you're going to have to get ready for that. It says two horses pulling a load. The chains between the horse and the load are an angle of 60 degrees to each other. Now, here, we don't mention that that means tail to tail, but it does mean tail to tail because that's the physical way that this plays out. If you have two chains pulling on a load, two horses pulling on the chains of the load, then the angle that it gives here, and it's 230 and 340, so I want to sort of get them to the right scale here. So we've got a chain pulling that way at 230 newtons, and then the chain pulling this way at 340 newtons. And they say the angle between them is 60, that means the angle goes right in there. There's no other place for it to go in that physical description of what's going on. And that's why last chapter we always said angle between them is always given tail to tail, because when the physical phenomenon come up in this chapter, that's where the angle is going to be. It's going to be between the two vectors. So if we want to add the two vectors, then we've got to slide this vector out. So here's the addition of the vectors here. Here's the 230 Newton force, and then I slide the 340 Newton force out to the end here. And I got to tell you, I don't really know how this all ends up. That's why I'm not being super careful about the diagram here, because the diagram's not really going to give me the answer. The math is going to give me the answer. So now I've slid them out to be tip to tail, because that's the way we add two vectors is tip to tail. Whereas before they were tail to tail, now they're in position to be added. But this angle out here, see, the angle of 60 is out here, outside. So the angle I want is 120 degrees. That's very difficult to set up that diagram. But the math is not too bad, because they want to know what is the resultant force, magnitude, and direction. I'm going to go after magnitude first, and the magnitude of this is given by c squared equals a squared plus b squared minus 2ab cos 120. So it's 230 squared plus 340 squared minus 2 230, 340, cos 120. And when I punch that all into my calculator, I get a c squared of, yeah, I got that now. And so when I take the square root of that, I end up with c equals 496.7 newtons. I'll leave it to you to type those in and make sure you get that answer. So that's the size of the force. Let's just check to make sure that makes sense. These two forces, two different forces are pulling on this, 230 newtons and 340 newtons. When we add those two forces together, they're not pulling in the same direction. So they don't get added all together because they're not just one behind the other. They're both pulling in a slightly different direction. So some of this force sort of cancels out. But when we add them all together, we do get more than each force individually. That is, we get more than 230 or 340. What we get is 496.7. Now, the angle, it says wants to know the direction as well. So I'm going to find this angle in here. And to find that angle in there, I'm going to give that spot a little label there. I'm going to call that X. And so that part of it's going to be sine law. I'm going to be 496.7 over the 120 equals 340 over this sine of X that I've got there. And when I cross multiply and do some work there, I get X equals 340 sine 120 over 496.7, but I got to sine inverse that whole thing. Maybe you need more steps there, and go through those steps if you need them. I get X equals 36.4 degrees. So my final statement is, therefore, the resultant is 496.7 newtons at an angle of 36.4 degrees with the 230 Newton force. Now, we're going to talk a lot about what reference we should use for our angles. In this particular question, there wasn't too many references to use because it didn't say whether these things were going north, south, east, west. The only thing we can reference is the original forces they gave us. The way I set up the diagram, it was easier to reference it off the 230 Newton force. I could have set up the diagram slightly differently and found the angle off the 340 Newton force. So that's sort of up to you. Equilibrium. Oh, huge idea here. Huge, powerful idea. In some case, an object is acted upon by forces but does not move. The objects are said to be in equilibrium. A little throw it to your physics people. That's when F equals ma, when you have acceleration equal to 0. And then you just use your regular kinematics equations. You don't need to go to F equals ma. F equals ma it gives you an acceleration. Anyways, we don't need all that right now. All we want from that is an object is in equilibrium if it's not moving. So the equilibrant is the single force that holds the system in equilibrium. It is a simple force that would exactly counterbalance the resultant force. So the resultant and the equilibrant must have equal magnitudes and opposite directions. If you're going to exactly cancel out a force or you're going to exactly balance it, you need to be the exact same size and pointing in the exact opposite direction. In the previous example, what would the equilibrant have been? Well, it would have been 496.7 newtons in the opposite direction. So a little more about equilibrium. When using vectors to model an equilibrium, the sum of the vectors is the zero vector. So when we add up all the vectors in the situation, we should get the zero vector. And for you physics people, we should get 0 in both the x and the y direction. So consider a traffic light that is suspended between two cables. You don't see many of these type of traffic lights anymore. It used to be that they'd hang it between two wires across between an intersection like this. In this situation, there are three vectors. There's the downward force of gravity. Gravity is pulling downwards on this lamp. Now, then the other vectors are tension in the one cable and tension in the other. These two cables are each doing some of the job of holding this up. They're pulling upwards and outwards. The two outward forces are balanced out, and the upward forces are balanced out. So those are the three forces. I'll call this the force of gravity. I'll use a little FG, and I'll call this tension 1, and I'll call this tension 2. This is a very common labeling system for these type of questions. Since the light is being held in equilibrium, the three forces acting on the light balance each other out. Therefore, if these forces were represented by vectors, the sum of the three vectors would be the zero vector. And a note about tension, the force of tension in the rope is always the opposite direction to the force pulling on the rope. So here, the force of tension in the rope is the opposite direction of the force pulling on the rope. So the force here is pulling this way towards the lamp, so the tension's pulling that way outwards. So consider the following diagram in which a 4 Newton weight is being suspended by an equilibrium by a string. This 4 Newton force, which has been blocked out here a bit, there's a 4 Newton force acting downwards due to gravity because of the weight, and then there's a tension, if it's going to be an equilibrium, of 4 newtons, and that has to be upwards. That tension has to be upwards to hold this thing in equilibrium. Okay, pretty common example here. At a school dance, the mirror ball is suspended from the ceiling by 2 wires that make angles 30 degrees and 20 degrees with the ceiling. If the ball exerts a 123 Newton force under gravity, find the tensions in the wires. I just need to mention that when we're talking about tension, we're immediately on our way to engineering type applications. This is huge type example when you're moving towards engineering. You'll use it in other areas as well, but this is really leans hard towards engineering. On the completed version of the note, I do this question another way as well, called resolution of forces. You physics people should pay attention to it and check out the resolution of forces method, because if there's more than 3 forces involved, you're probably going to need resolution of forces, not this method. This is a nice method to handle 3 forces exactly. So I'll call this method 1. And I'll say this year that method 1 will get you there anytime there's 3 forces. So this is called triangle of vectors. And I'm going to say tough picture. It's going to be tough to set up the picture for this. I'm going to say 3 vectors works best. And I'll say the math is nice. It's going to be nice math once we get the picture all set up. If you're going to move on into physics and so on, then you may want to look at something that it can handle 4 forces set up, and you'll need what's called resolution of forces. That method is highlighted on my completed version of this note, but on the video here, I'm only going to do the first method. It will handle anything with 3 forces. Let's be very, very careful to set this up so the picture is obvious, because once I have the picture, I'm telling you the math will be very straightforward. It says find the tensions in the wires. We want to know how hard are these wires being pulled on. Because if we're going to bounce this disco ball down, we don't want either of our wires to break. And so we want to know how much tension is in each wire. And then we can test out our wire and know, okay, it can handle that much tension. Then we can hang this thing and feel safe that it's not going to break. So, tensions in the wires. Here are the important forces we got to talk about. Along this wire here is tension 2, I'll call it. Because along this wire here is tension 1. There's 2 of the 3 forces. And as I was introducing this example, you might have went, what 3 forces are you talking about? I only see 2 wires. There's a third force here, which is the force of gravity on this ball. So those 2 tensions have to exactly cancel out the force of gravity if this thing's going to be in equilibrium. You say, well, I don't see anything in this question that says it has to be in equilibrium. We're hanging this mirror ball up on top of a dance floor or something like that. We don't want it to move. It can't move up, move down, or that's bad. It can't be rolling around on the floor. It's got to be sitting stable at the top. So sometimes the word equilibrium is not in the question. You just have to recognize from the problem that, oh, this thing's not moving. It's hanging there. And so maybe when it says is suspended from the ceiling, that's your clue that we're talking about equilibrium. Now, this diagram is very difficult unless you do this first thing. If you've got a horizontal or a vertical force, draw it first. And so here it comes. Here's my diagram of the forces. There's the force of gravity being pointed straight down. If you get that onto your diagram, the rest is pretty straightforward. I'll switch to my fancy purple color. Because take a look at tension 1. Tension 1 is pointed in this direction here. I'm going to highlight that again, and tension 2 is pointed in this direction there. But if it's going to be an equilibrium, those two tensions have to add to the force of gravity. They have to perfectly match with the force of gravity here. That means tension 1, which is sort of in this direction here, and I add that together with tension 2, which is sort of in this direction right here. And I don't know if I've drawn it perfectly well to scale as far as the size of all these vectors are concerned, because that sort of looks like it comes out to a right angle, and I have no idea whether it comes out to a right angle or not. And that's not the point of the whole question. The point is that tension 1 and tension 2, if it's an equilibrium, have to add perfectly to the force of gravity. Or said another way, these two tensions and the force of gravity, when you put them all together in a triangle of vectors like this, that should come out to the zero vector. It has to perfectly be in equilibrium, so these vectors have to cancel each other out. Okay, I said the diagram was tough. That's the tough first step, is to get any horizontal or vertical forces on there so that you can draw the triangle vectors easily. Once you get used to them, you won't need a horizontal or vertical reference force. You'll just draw the three vectors on the page sort of to scale and go, okay, I know this is the way it's got to play out, but they've all got to cancel each other out. Then you got to get the angles on. Not easy. Tension 1, the top of the arrow right there, makes an angle with the horizontal of 30. So I'm just going to put a little tiny horizontal on there, and I know tension 1 has to balance with that with 30. Tension 2, the end has to have a 20 on there. And can you see the Z pattern in there? Let me just get the highlighter out, and I'll erase this right afterwards because I don't want my diagram to become too messy, but there's a Z pattern right in there. And the Z pattern is very, very helpful here. Oops. There it is. Okay. And I want to undo. See if I can get that back there. There we go. And so what I end up with is a 20-degree angle in there as well. End result, that whole angle there is 50 degrees. Not even close to 90, which is what my picture sort of represented. But you see, I wasn't trying to get the picture exactly right. I was just trying to get a picture that I could work off of. Well, if you get to that phase, that's the difficult part of the diagram, is getting that all on there, because tension 1, we knew, they told us that first tension, they didn't tell us the first tension. They told us that this thing comes out to, this force of gravity is 123 newtons. That's what they did tell us, was that force of gravity is 123 newtons. But we've got some angles we can work with in here now. That's a 50. That's a 70 in there. And so now I'm going to go after tension 1, just using sine law. The magnitude of tension 1 over sine of the angle there, 70, has to come out to magnitude of, it has to come out to the 123 over the sine 50. Those are the things we were given. And I'll let you do the rearranging there. But tension 1, after you do the rearranging here, is going to come up to 150.9 newtons. You go 123 sine 70, and then you divide by the sine 50. Next, tension 2. To get tension 2, we use sine law again, and it's tension 2 over sine. Ooh, I don't have that angle yet. Let's see, 70 and 50. This is going to have to be a 60 in there. So tension 2 over sine 60 equals 123 over sine 50. I'm using that same angle pair there, and when I rearrange that one, I get tension 2 equals 139.1. Again, it would be 123 sine 60 divided by the sine 50. I just have to rearrange that with a little cross multiplication. So I like this method for three vectors because once I have the diagram, finding the actual size of the vectors is not too difficult. But you got to do a very careful diagram on that, and that takes some practice. So when you get to the homework questions like this one, come back to this video and carefully walk through how I set up the three vectors there. Now, resolving vectors. What you found out there was that vectors that can be broken up into different directions there. And so moving forward, we need to be able to resolve vectors into any directions we want to. And so that's what the resolution of vectors method does, is it takes those vectors and breaks them into two pieces, an x component and a y component, and you should take a look at the completed version of that to talk a little bit more about how we would resolve vectors. Basically, though, all we're trying to do is say, listen, if we're given a vector like this, 90 newtons, we can break it up into whatever directions we want. Here, for instance, I'm going to take this 90 Newton force and see how much of it goes in this direction here, and this 90 Newton force, and see how much that force pulls in this direction here. And the same with this one, this 90 Newton force here, which it doesn't show very clearly on there that this is a 45 and a 45. So we want to know how much of that is this way at 45 degrees and how much of that pulls in this direction at 45 degrees. So actually, it looks like it's complicated, but it's really not. If I want to find this force in this direction here, and I'll call it a force in the A direction, and I'll call this one force in the B direction, I'm really just doing a fairly simple application of trigonometry here. If I want to find the force in the A direction there, the direction indicated, I'm just going to call cos of 60 degrees equals force in the A direction divided by the hypotenuse 90, and so I get force of A equals 45 newtons. And then if I want to find the force in the B direction, cos of 40 this time, and it won't always be cos, it just depends on how your diagram's set up. It happens to be cos here because both forces I'm trying to find are adjacent forces. So I want to find force of the B over the 90, and I get force in the B direction equals 68.9 newtons. And then in this question here, both forces happen to be the same because it's a 45-degree angle here, and so I'm going to call this force in the x direction, just as a throw to you physics people there. We're trying to find out how much of this 90 Newton force acts along this line, and so cos of 45 equals adjacent over hypotenuse, and so I get force in the x direction equals 90 cos 45, and when I type that in, I get force in the x direction equals about 63.6 newtons. Okay, so that's all resolving force is about, is find out how much of this force goes into a certain direction. Oh, and because of this situation being a 45 degree, and that wasn't made really clear on the diagram, the force in the y direction is going to be the same because it's a 45. Okay, now listen, I know that resolution of forces example that's in the completed version of the note is not covered here, but I encourage you, and I would say that no matter how this class was set up, I would say go and do some of these questions first using the triangle force method, because when you can set the triangle force method up properly, what you'll find is that'll be quicker and easier. The diagram's a little bit difficult, but it'll be quicker and easier. The only reason to do resolution of forces is if it's more than three forces, and it's all three force examples here. Okay, so there's force as a vector. I'm telling you, take a run at this homework. Follow up with questions if you have any, because things are starting to ramp up. So if this seems really difficult, well, it is really difficult, but things are going to